morning. It's a sad day when I can't be with you again. I know, I miss your faces, but you don't miss my voice. Our lesson today is going to be page 13 in your packet, and then page 17 in your packet. So if you need to pause to get everybody in this situation to be ready to take notes, then please do so. We're going to talk about exponential models still. I think you're going to find today to be fairly easy. This is page 13. So it says there are many examples of growth in the real world. We've talked about that. So exercise 1 is it talks about a population of fruit flies growing at a constant rate of 6% per hour. The population starts at 0 with 28 flies. So basically what we have here is we have a point that's 0, 28 to start. So at hour 0, there's 28. So in order to fill out A, it says, using what we learned in the last session, determine the population after each of the following amounts of time, show the calculation, and you use a repeated multiplication. So you started out with 28. Let's remember that exponential functions start out with the original times the growth rate to the exponent of x. So in this particular case, the growth rate, remember, is 100% of what it was before plus another 6%. And when we change those to a decimal, you get 1.06. And so this is after the first hour. So the x value is the hour. The x is the hour. And so they're calling it t, but for our purposes of the exponential function, I'm just saying the word x. So this is to the first hour. And then you plug in the answer to that, and it grows at 100% plus 6 more, but this time it's 2 hours. And then the answer to that goes 100% plus another 6% for 3 hours. So in your calculator, we want to go ahead and do that. So we have 28 times the growth rate, which is 1.06, and we want that to the first power. So after 1 hour, it's 29.68. So in this particular case, oops, sorry, I just opened up the wrong page. My bad. So we have 29.68. So after the first hour, that's how many fruit flies there are. That number now goes here because the second hour starts out with more flies than the first hour. So now again, we go into our calculator. We take that answer. I personally am just going to copy it. We know that the growth rate is still 100% plus another 6%. This time, though, we are at the second hour, and so that becomes 38.348448. So on our paper, we certainly can abbreviate a little bit. Well, if I could remember the answer, 33.348. But please remember that really in our calculator, we're plugging in what was there before, but we're just actually copying that so we don't round so early. So 33 I'll put 0.3, but really in my calculator, I'm going to come up and copy that, still multiplying that by the growth rate, which is 100% plus another 6% to the third hour. And so it's 39.7, let's say 2. So 39.72 after 3 hours. So about 40 flies, right? About 40 flies. Hopefully I did that correctly. If you got something a little bit different than that, please make sure that you're checking my work. So for the second question, part B, it's asking us, based on part A, find a formula that models this. So remember, our main formula looks like this. That's our main exponential function. Really, they're asking us to find a function for the population. So the population based on the hours, so P of t, the initial starting amount of flies was 28. The growth rate was 100% plus another 6%. and that's to a certain amount of hours, which they call T. So please remember that we want to just plug in. The question for part C says, what is the value of 24? So that's saying after one day, how many fruit flies are going to be in that particular vicinity, and it's kind of nasty. Yeah, so we've got 28 fruit flies growing at 100% plus another 6% every hour. Ugh. And we want that for a full day, which is 24 hours. We're talking 113 fruit flies. About. I don't know if I want 113 fruit flies flying around me, but that's the general consensus. So now the next two, and I'm going to try to go back and forth between slide pictures. The next two questions, as you can see, part D says, what is the range? And part E says, let's make a graph of this. So for me personally, I think I want to make the graph first. And so it's asking us to sketch a graph over the interval where the hours, which is really our T or X, it's the X-axis and the Y-axis, but they're talking about these in terms of P's for population and T's for time. So it's asking us to go 0 to 24, so for hours, and so I might just divide this by 4. So 4, 6, 10, and you keep going up. So 14. I might run out of a little bit of room. Oh well, if I can count by 4s, it might help me, right? So 4, 8, 12. Oh, there we go. 16, 20, and 24. Well, there we go. If I could count, like, would be great. And then it tells us to go to 120. So you've got a fairly large thing here. I don't know if we can fit it by 10s, but maybe we can go by 20s. So let's see, 20, 40, 60, 80, 100. Yeah, we're a little off, but that's okay. 120 about right there. We go to graph this. We know at 0 hours it started and it had, what, 28? So maybe something like right there. That was 0, 28. And then after 1 hour, this might be a little bit kind of, we should stretch this out a little bit more maybe. But after 1 hour, the flies go up to about, I think we said 33, so maybe like right here. So it's kind of going to jump up like this. But after 24 hours, my graph is so very wrong, but after 24 hours, there was something like 113. And remember, an exponential function, sketch doesn't have to be perfect, but it kind of goes like this. A range says the how tall part of the graph. And so the range, it starts out at about 28 flies, and the range is the Y value, or in this case, the P of T value. And the range in that particular time, it stops at about 113, says for the domain. So let's do this. It was 113 point something, so let's talk about this. Domain of 0 to 24, it was 113 point something, so it's not quite 114, it's a little bit less. And that's the graph for that. I think we've done this numerous times. The last question on this particular page says if the savings account is modeled by this particular equation, which of the following is true? So before I even look at the choices, I want to make note that the 250 is what I started with. That's the money start. And this means that I'm growing at 100% plus, now remember this decimal needs to be slid over a little bit, another 4.5%. If I have that, it should be fairly easy to find that the amount deposited was $250 and the rate is 4.5%. Your job on this particular lesson is to finish pages 14 and 15. Page 14 is the same thing, only a decline or a decay. increase. I'd like you to go right to page 17 now. This should be very, very simple for you. Go to page 17. Again, if anytime you need to pause, please do that. Page 17, we need to talk about the difference between linear and exponential. So please remember, linear functions are y equals mx plus b, and the y values are constant. The y values are usually added and subtracted in a constant pattern. The exponentials have the general equation of a b to the x. Exponentials, key words are multiply, double, interest. Again, if you need to pause to make sure you're all getting these notes, please do that. And again, the y values don't have a constant. The y values pattern, not constant. It's not a constant number. So again, pause if you need to. In taking a look at this, if you look at your y values, it's plus 5, then it's plus 10, then it's plus 20. The constant is not the same. Really what's happening here is we're multiplying by 2 every time. So this is going to be an exponential function. It's an exponential function where the equation, the initial is 5. The pattern is a multiply by 2, and it's to the exponent of x, because every exponential function has an exponent of x, right? Repetition, alliteration. When we go to the next one, if we take a look and do the same exact thing, this time the pattern is plus 3, plus 3, plus 3. So we want to use our slope-intercept. In this case, the y-intercept. So this is linear, sorry. This is linear. The y-intercept is positive 8, so that's your b value. The slope is the change in y over the change in x, and we know the change in y is 3. Always the change in x is plus 1, so we have 3x plus 8. And I believe these answers go down here in this particular spot. So that's our job, really, is to determine the difference between the linear and the exponential functions. The last question I just want to touch base on, and we will be seeing these, you need to do, it says create a linear equation that passes through those points and an exponential equation. So first, the linear equation, we've got the points, remember, here's your x, here's your y, here's your x, here's your y. So it's telling us the y-intercept is 12, and the slope is the change in y over the change in x. So 12 minus 3 is 9, 0 minus 1 is negative 1, so that slope is negative 9 twelfths. 9x plus 12, sorry. If I sketch that, let's say that this is about 0, 12 right here, and we have down 9 over 1. And we keep going, so this line would look something similar to this. Again, it's a sketch, so we don't have to be perfect. The exponential function tells us the same thing, except this time the starting value is 12. And when we're doing this, it's a 12 divided by 4. So it's really multiplying by 1/4 to the x. When you graph this on your calculator, the y-intercept's going to be the same, and it's going to look something similar. Ooh, that's a terrible one. Your sketch is going to be better than mine. Something similar to that. It's not really asking you to do too much other than look and notice that you can create a system of equations. Please go ahead and continue working on your Regents review that you have, and also do pages 14, 15, and 19 in your packet. I miss you, but have a great weekend. Talk to you Monday. See you later.